Hi, my name is Ankit Kumar, and I'm a high school student who has been working with a research group led by John Kovac at the Harvard-Smithsonian Center for Astrophysics. John Kovac's team is currently on the forefront of cosmology research as they try to explain the large-scale structure of the universe as well as try to determine what happened in the first few moments of existence. The key to the research is probing the information contained within the cosmic microwave background, or CMB for short. Notably, the detection of specific polarization signatures within the CMB may corroborate the theory of inflation, a period of exponential expansion of the very early universe. These concepts will be explained briefly, but if you would like a detailed explanation, you can find it here. The continent of Antarctica, a massive expanse of snow and ice. In the winter, temperatures can dip below -80 degrees Celsius. The landscape is remote and desolate. Yet, despite the challenges of the environment, the South Pole is actually the site of cutting-edge research on the early universe, and is ideally suited to observation of the cosmic microwave background. In fact, telescopes located at the Amundsen-Scott South Pole Station are currently producing most detailed maps ever made of the cosmic microwave background polarization. If you'd like to explore the Amundsen-Scott South Pole Station in Google Street View, click the image currently displayed. The CMB is radiation left over from the Big Bang, and the earliest direct observation that we can make of the universe. Remember that as we look out into the universe, we are really looking back in time. For example, the Andromeda Galaxy is 2.4 million light-years away, meaning that its light has taken 2.4 million years to get here, and we are seeing it as it was 2.4 million years ago. Theoretically, one would imagine that if we looked far enough out, we would be able to see the Big Bang itself. However, we hit a wall. That wall is the surface of last scattering, and it is the point at which the universe had cooled enough to allow photons, or light, to pass through it unimpeded. The radiation we receive from the surface of last scattering is the cosmic microwave background. The CMB is composed of two main components of interest to researchers: temperature and polarization. The temperature of the CMB is remarkably consistent in every direction we look, approximately 3 Kelvin, or barely above absolute zero. However, there are very minute differences in temperature that arise due to quantum fluctuations in the early universe. These differences in temperature are so small that they were not detected until nearly 30 years after the first detection of the CMB. The polarization of the CMB is even more faint, about 10% the intensity of the temperature fluctuations. It was not until 2002 that the DAISY experiment at the South Pole detected polarization. To learn more about the surface of last scattering, the CMB's temperature fluctuations, and polarization, use the following links. Certain patterns of polarization in the CMB, if detected, will prove the theory of inflation as the correct explanation for the current structure and geometry of the universe. The theory of inflation suggests that in the very early stages after the Big Bang, the observable universe underwent an immense period of exponential expansion that ended when it was approximately 10 to the 26 times greater in size. The theory was first proposed to explain a number of peculiar features about our universe. To learn more about inflation, click here. Given the challenges of the environment, you might ask why anyone would bother to spend months on end observing the South Pole. The answer to this question can be seen quite clearly visually. What you are viewing here is the sky as it is seen from the South Pole. Shown here is the sky in infrared wavelengths. The chief source of this infrared radiation is interstellar dust. It is the very same dust which severely interferes with the measurement of the CMB. The South Pole sky provides an ideal window, delineated here, that is relatively free of interference. Furthermore, the South Pole is fully immersed in darkness for 6 months of the year, allowing for uninterrupted observation during the winter months. Located at an altitude of around 10,000 feet, the South Pole Station is also cold and dry, with relatively stable atmospheric conditions. For several decades now, it has been the prime choice for ground-based CMB measurements. BICEP, which stands for Background Imager of Cosmic Extragalactic Polarization, currently has the best published maps of the CMB polarization. BICEP finished observation in 2008 and was followed by BICEP 2, which has more detectors and higher sensitivity than its predecessor. The successor of BICEP 2, which is already in operation, is the Keck array. The Keck array is composed of 5 copies of BICEP 2 in an array arrangement to increase speed by a further factor of 5. The general design of all these telescopes is roughly the same. As previously mentioned, the signal of polarization that needs to be measured is extremely faint. Any interference or noise could easily drown out the signal. Any source of heat is capable of emitting electromagnetic radiation that could contaminate the signal from the sky. To minimize interference, the telescope is cooled in stages to just above absolute zero using a liquid helium system. Furthermore, the interior of the telescope is kept in a vacuum to prevent condensation and ice crystals from forming and ruining the sensitive instruments inside. Shown here is the WMAP survey. WMAP was a probe launched in 2001 by NASA and captured a full-sky survey of the CMB. The different patches of color represent temperature differences, redder areas being hotter, bluer areas being colder. Remember though, these temperature fluctuations are incredibly small. The coldest regions are only several hundred microkelvin, cooler than the hottest regions. If you would like to explore the WMAP data on your own, feel free to pause the tour and select WMAP ILC 5 year from the drop-down imagery menu at the bottom of the Worldwide Telescope interface. The South Pole instruments cannot produce an all-sky survey. They observe only in the ideal observing window shown earlier. BICEP's temperature map is shown here. The two different temperature maps have been taken at two different frequencies. Here are the polarization maps. The white bars are polarization vectors, mapped over the temperature maps already shown. The color scale of the temperature map has been changed to increase the contrast. The length of the bars represents the magnitude of the polarization, or essentially the percentage of light from that particular area that is polarized. The orientation of the bars represents the direction in which the light is polarized. Here is BICEP 2's polarization map. This is the most sensitive map of the CMB polarization produced to date. Remember that if you would like to explore these maps on your own, you may pause the tour at any time and select the BICEP data from the All Sky Survey folder under the Collections tab at the top of the Worldwide Telescope interface. Although we have measured polarization of the CMB, we have not yet measured the pattern of polarization that would prove inflation. At best, current experiments can only constrain a maximum value for how strong these polarization signals can be. However, as Keck continues its observation and future instruments with even more sensitivity become operational, the goal of validating inflation is within the grasp of cosmology. Such detection would not signal an end for cosmology, however, but a new beginning. The future of this field is looking to be just as exciting as its past has been.